this afternoon session will be done by Dr. Rafael Aránguiz from Catholic University of Concepcion in Chile.
Okay, good afternoon. Thanks for attending this presentation. I would like to present some results of a 3-year research project I've been doing in Chile. And this project is about tsunami resonance, so I will explain some results of a particular small bay in my hometown. This is a work of a undergraduate student. So when the 2011 tsunami happened in Japan, it traveled from here to Chile. It took approximately 24 hours to arrive to Chile. So this is the study area in the central part of Chile. This is the 3 bays I'm studying in the project. So I have the Concepcion Bay, which is the largest bay, and then San Vicente Bay, and this is Coliumo Bay, where the Chato town is located. The Chato was flooded in 2010 by the Chile tsunami, and also in 2011 by the Japan tsunami. So the tsunami traveled from here to here 24 hours, in 24 hours. Well, when I traveled from Chile to Japan, it takes almost 40 hours by plane. I think tsunami is smarter than airplanes. And well, what is important here is 2 meters in Talcahuano, here in the large bay, only 2 meters, and 4 meters inside this area. So this 4 meters was large enough to flood all this area. This inundation area is very similar to the inundation area in 2010. So I could say that after 2010, the authorities wanted to buy all the houses and relocate people. And they didn't want to sell houses because this is a beach area, very expensive and very touristic area. But 1 year later, after 2010, this 4-meter tsunami inundation helped government to buy the land and houses because people in 1 year experienced 2 inundations. I also want to mention that in 2010 is 6.5 meters in Talcahuano and 7.5 meters in the Chato. And 1860, in a little bit to the south, was 3 meters in Talcahuano and from 3 to 5 meters in the Chato. This is the 9.5 magnitude. So, but when we go to the history and check what happened in past events, we see that in the Bay of Concepcion, in Talcahuano, it's very often to find this 3rd wave, which is larger than the previous 2 waves. The same in 1751. So the 3rd flooding being the most severe, and 1730, there were 3 large flows, the second of which was larger. So it's very common to find this kind of description that the 1st wave is not the largest one, but the 2nd or 3rd one. So maybe there is some effect that we would like to investigate. In addition, I would like to explain this, the objective of this study. So we would like to identify some tsunami resonance during to this event, which explain the large inundation compared to other bays. What we did was to simulate this 2011 Japan tsunami using the NEO-wave model with 4 nested grids. The higher grid resolution was 30 meters, which included both bays, Columo and Concepcion Bay. We simulated 42 hours of elapsed time, which took almost or around 2 months. So you can imagine, after 2 months running the simulation, if something is wrong, you have to do it again, so it's 2 months again. And then, after the numerical simulation, we computed the natural oscillation modes using the Bellotti et al. Equations, the model used in finite element method, with 3 different domains. Then we applied this Rabinovich method to compute the background spectra from tide gauges to identify some oscillations without the event. In addition, we simulated 2010 tsunami, and we were quite lucky that when the same day we installed deployed the pressure sensor, the tsunami happened in Coquimbo, so we measured for the first time a tsunami inside the bay. So we also compared these results. When we talk about resonance, I think we could be quite familiar with several physical phenomena, like the voice with the glass, this game, the wind in a bridge, or structures. So we are quite familiar, and we understand that when the frequency of the forces of excitation is similar to the natural oscillation mode or natural frequency, we have this increase in the amplitude, and we have the resonance. In the case of the bass, we can explain the resonance with this simple video. So please pay attention to this small swimming pool compared to the large one. This is 2 swimming pools inside a vessel, a cruise, okay, which is subjected to the waves motion. So this wave motion excites the oscillation modes of the 2 small bays represented by these swimming pools. If you see this compared to the other one, it is the same motion. The vessel is applying the same frequency to the 2 different swimming pools. So this phenomena inside a vessel could be quite funny or quite dangerous, right? If you know how to swim, it's funny. So now we understand a little bit this resonance phenomenon. I will show you the results of the study. First, the numerical simulation. So we ran this simulation. After 20 hours, the tsunami is already arriving to the Chilean continental shelf. We compare the results from the numerical simulation with the records. Actually, this simulation was done by Bay et al. And already published, and they compared with the dart buoys along the Pacific Ocean. So what I did was here to include more grids, higher grid resolution in the Chilean side, and I compare in Talcahuano, for example. So after 2 months running the model, when you get the results and you see this, it's not possible to explain in words what you feel, right? When you compare the spectrum, it's very, very good, actually. And this is the measurement inside the channel. So you see the 4 meters is quite well, and not the first and the second wave, but the 4th wave. And this is the the tsunami spectrum. So with these results, we analyze and continue doing the results. What we do is, here is, we deployed the pressure sensor, and we measured tides during at least 3 months. Here I showed you some 3 weeks of measurements. We use a 24 hours window to compute the spectrum for 24 hours. So the gray lines are the individual spectrum for 1 day, and the blue are the average. Is the average of the whole spectrum. So from here you could see some peaks of energy, okay? So we want to see whether these peaks coincide with natural oscillation modes. So what we did then was compute the natural oscillation mode. These modes are computed from just the bathymetry, no event at all, only the bathymetry. So we have a, maybe you cannot see very well, but this is 116 minutes, 99 minutes, and 72 minutes. So you could see different shapes of the oscillation modes. I didn't show here the phases. With the phases, you can understand much better how these modes behaves. Here we have 59, 56, and 46. Columo base is here, so you could see this, for example, is quite important in Columo, also the 72 in Columo. A smaller domain, we also include this, the 3 bays, so we have 95 here, 38, 33. We also have this in the small bay. And then we also see some combination, some multiple resonant effect, multiple resonators effect. So 27, 24. And now we also computed only the small bay, just to see better this fundamental mode of the bay, and 15 minutes mode, 9 minutes, 8 minutes, 7 minutes. So what we did next was try to combine all the results. Measurements, tsunami simulation, background spectra, and natural oscillation mode in one figure. And we have this. So this is the black line is the average spectrum of is the background spectra. The vertical lines, the black lines, are the oscillation mode from the larger domain. The red lines are from the medium domain, and the green lines are from the smaller domain. And here we have the measurements. This is the 2015 tsunami measurements. So, for example, here, what is really interesting is this 24 minutes, which is the fundamental mode. This one is present here in the background spectra. It's also present, very large energy in the measurement in 2015. It's also present in the 2011 simulation. We also have this peak here, and also this, the 72, is this mode. Okay, so with this picture, we can analyze, or we can try to explain why we had this very large inundation in 2011 tsunami, because most of the energy coincide with the oscillation modes, which combined both the continental shelf and the bay oscillation. Not only the bay, the domains relate, the oscillation modes related to the bays are this one. So you see it's very small energy compared to the energy which include the oscillation modes in the continental shelf. So what we can conclude is, well, we could simulate this, the 2011 Japan tsunami, which agreed very well with the measurements. We also computed the natural oscillation modes in both the continental shelf and the bay. We measured tidal variation and computed this background spectra. And then the energy peaks of the background spectra and tsunami events coincides with natural oscillation modes of the continental shelf and the bay. This is one of the most important findings in the research. So finally, we can conclude that large inundation in Columo Bay was due to tsunami resonance, since the tsunami excited not only the fundamental mode, but also several shelf oscillation modes. Therefore, there is a combined effect of this shelf resonance and the bay resonance. Thanks for your attention.
Very much. And I have two questions about your tsunami warning system. The first question is that since the resonance of tsunami or oscillation of bay is very important for prediction of tsunami height, So this oscillation effect is included in your warning system or not?
Well, it's not included yet, but with another researchers, we are trying to build an atlas of the resonance along Chile. So with this kind of atlas, we can identify the more affected places. So for example, here, when we see this figure, we see that the Bay of Concepcion is very affected by this kind of resonance compared to the other small bay. So when a tsunami happened, we know that with this result that this bay could be affected because there are more oscillation modes which include the bay.
Okay. And my second question is that it takes almost 24 hours after the earthquake. So you had enough time. How was the behavior of coastal residents against this tsunami event?
Well, I think thanks to the 2010 tsunami, the behavior was much better in 2011. Well, we have these two situations. First, 24 hours, and second, the tsunami the year before. So the behavior was quite okay for people, and the tsunami warning system also was a little bit improved in 1 year and worked properly at the time. So people evacuated. There was no any casualty, only some damage on fishing facilities. But in general, people evacuated the whole country. No problem at all.
Okay, thank you. Any other comment or question? Yes, please. Dr. Nagai.
Hi, thank you very much. My name is Nagai of ECO company. At the beginning of your presentation, you show the comparison between the observed tsunami profile and simulated tsunami profiles. And I'm surprised the peak time, first wave peak time in Talcahuano and also that buoy coincide very well. But in our experience of 2010 tsunami or the case, the traveling time of Pacific Ocean is very difficult to predict precisely. So how do you adjust the peak time of the comparison in this figure, please? Thank you.
Oh, thank you for the question. Actually, I forgot to mention this in the presentation. There is a small trick behind this, because you're right, it's very difficult to get the right time or arrival time, because the models doesn't consider elasticity and other kind of physical phenomena. So what there is, if I remember well, there was a 15 to 20 minutes difference between the simulated and recorded arrival time. So we extended, we multiplied by a factor in order to extend the time series and match the arrival of the first wave. So why we did so? In order to get this figure. So it's not just moving the time series, it's extended. It's okay?
Oh, okay, thank you very much.
Any other question or comment? All right. Okay, thank you very much again.
Okay.
So next presenter is Dr. Ravindra Jayaratne, who is teaching at University of East London, UK.
Thank you, Prof. Shibayama. Good afternoon, colleagues, guests. Ravi Jayaratna from University of East London. For the last two occasions, in 2009 and also 14, I delivered the talks on the tsunamis as well as sediment transport. For this time, I thought I would take a case study from UK. Yeah, I'll give you an overview about the Humber estuary anyway, I mean where it is located and so on. So the title of my talk today about the hydraulic performance of grass-covered the levee flood defense structures against the predicted climate change. And we have taken, I mean, as a case study, so we looked at the flood defenses in Humber estuary or defenses located in Humber River. The outline of my presentation, I would like to give you a brief overview about the project context or the motivation for this particular study. And then we have set three project aims, which could be, the doable, because I forgot to mention that this is one of my MSc students' work. Then in my presentation, actually, I would like to go through the assessment methodology, pretty much about 10 slides based on that, and also sometimes you would feel a bit bored because you have actually listened very impressive, very eye-catching, the slides with a lot of images and so on. The mine is pretty much about, the tables, data, and so on, okay? Sorry about that, and I do apologize. Finally, I would like to, summarize conclusions, and also there are some limitations. Of course, there are some people behind the screen, so I would like to acknowledge them. Right. The country like Britain, so we are more prone to coastal and fluvial flooding. So if you look at the British history for the last 100 years, pretty much I would say since 1910, the December 2013 up to April 2014 were the worst the period for Britain. So we have got about 12 odd winter storms, quite severe winter storms in the country, and also these were, they were fallen somewhere around northeast as well as the southwest of England. So I'm pretty sure you all know that, the Britain, we have 4 countries, Northern Ireland, Scotland, England, and Wales. So pretty much, the places or the locations in England were affected by the winter storms. In this particular winter storm, as I said, my main focus is the location in the northeast of England. About 30 properties been, flooded, and also about 2,400 hectares of agricultural land being, inundated and so on. So the flood levee structures, they were overtopped particularly. We have 2 main government bodies in the country. The first one is the Environment Agency, where they look at the coastal flooding, whereas we have another organization called DEFRA, which is the Department of Environmental, Food and Rural Affairs, where they look at the coastal erosions. It's unlike in the other countries, back home in Sri Lanka. So we have one organization, which is the Coast Conservation Department, but in Britain, particularly in the Wales and England, so we have Environment Agency and DEFRA. So what they have done, so they have commissioned a post-disaster field investigation, particularly to prioritize any remedial works to be done in order to, the smooth running of the day-to-day life and so on. So then in terms of the investigation, what we found is that the failure of the defenses occurred because of the poor quality of the flood defense structures, pretty much about the poor condition of the grass reinforcement cover. And also, as you all know, that once it is failed due to the rapid erosion, particularly because of the losing the shear strength of the material. And the more structures are earthen, they are loam substrates where the sand is mixed with silt and clay. The project aims are looking at the hydraulic performance, particularly the wave overtopping and wave overflowing of the defense structures, again the increased water levels and wave heights. And also we looked at, as I said, if you look at the title, we looked at the plain grass reinforcement. If you look at in a minute, you will see some photographs. So normally the seaward slope as well as the other slopes, the both were covered with the grass as well as the reed beds, reed material or the reed plants. Then we assess the wave dissipation, actually the effect, and also subsequent reduction in overtop in overflow provided by the reed beds. Right, I'm pretty sure you know where the England and then the Britain is, and that's where the study location, and then this is located in the two counties, the Lincolnshire and in the Yorkshire. It's about 340 miles from where I live. I live in London, East London, so it takes about normally 3 hours 40 minutes to get to the site. Yeah, so that's the Humber River. You can see. So that's the Humber estuary actually. So that's the Humber, the bridge. So that's our study location. So it's about 3 kilometer stretch from the Barton upon Humber all the way to the Barrow Haven. So this is, we call it actually the Barton Barrow Trail. So that's the one so we looked at. So what we have done, we have taken 7 sections between, I would say, about maybe 250 to 300 meters the width. Okay. Right, so that's a clear picture for the inundation of the agricultural land. About, as I said before, it's about the 1,400 odd the hectares been inundated. So these are actually the 4 slopes being covered with the grass, reinforcement of the grass, as well as some the reed beds. So as you see, I'm sure, I mean, some of you already work on the vegetation. I mean, particularly about the damping or the wave attenuation effects on these type of, the structures. So normally these structures were colonized on the wet surface all the way up to the dry the ground. Right. Looking at the quantifying impact of climate change. So what we have done, so we have taken some the predicted water levels with a return period 1 to 1,000 from the Hydraulic Research Wallingford. They have already have done the analysis and then they have gathered. So we have taken that. So they were quite generous to provide that data set to us, to my student Lee Sensia. And then, so what we found is they have insufficient the wave heights, so that, I mean, in order to do the annual maxima distribution or the Gumbel distribution, so that we had to go for the hind casting technique to apply the Jones-Swap TMA. I'm pretty sure, I mean, because you have already, some of our colleagues, they have talked about the Jones-Swap TMA and so on, so that by using that, so we were able to get the shallow water, the wave conditions, wave heights, as well as the associated wave periods. So that's what you have seen. So what we have got from the Hydraulic Research Wallingford about the return periods all the way from 1 to, I would say in this particular case, this is an example, the 500, and then we have the best estimate and also the 95% upper and lower confidence intervals. The Humber Ports Authority, so they have given the bed levels. Actually, initially what the Hydraulic Research Wallingford gave us the elevations and then the bed levels, so that we had to do the corrections to get the water levels and so on. So after that, we have used the normal statistical analysis. So basically, the highest rank to the lowest, and then, so these are the return period, cumulative density function, and also we have the minus of natural log. So basically, the idea is to plot use the Gumbel distribution. So the wind, the maximum wind speed against the Gumbel reduced variate. So that's where we have the good fit, of course, with the data. And then, again, another important thing is the direction of the fetch length, basically how the wind blows over the surface of the ocean and across. So these are the sections, as I said. So within the 3 kilometer stretch, we have taken 7 sections, 1 to 7, and then these are the fetch length. And okay, so I think I forgot to mention about the design scenarios we considered. So we had some limitation of this project because we have never looked at the joint probability distribution. So what we have done, so we have as a best guess, so we have taken some different combinations. So you will see here the 100-year return period of water depth combined with the 1-year return period of wave height and so on. So these are the 4 possible scenarios we have considered. And you have seen the wind direction and so on. And yeah, so these are the design scenarios: 100 return period of water depth, water depth, wave heights, and then so these are the based on the wind direction, so the values we obtain. So, and then about the critical hydraulic failure, so we'll check the Eurotop manual. So about, I mean, not the latest one, because latest one was released in October 2016. So we looked at the 2007. So the two worst case scenarios, the overtopping with the positive freeboard and also the overtopping overflowing with negative freeboard. Again, the return periods we chosen for the water depth and wave heights. So these are the estimates we have got from the probabilistic analysis. Right. And so about the external hydraulic processes, we never looked at the internal hydraulic process, we looked at the external. So we had the two worst case scenario, the overtopping as well as the overflow. And also we used the typical Owen's formula. And also, as you know, that for the overflowing, so we have a slightly different formula with the irreverent number, the wave height, and then the freeboard and so on. Right, and then we use the flood and reservoir safety manual authored by Institution of Civil Engineers. So what they have done, so based on that, so we have the different flow regimes, of course, I mean, because these are classical hydraulics like the subcritical, supercritical, and so on. So we have the erosion zones like 1 to 4. The most critical would be actually the 2 to 4, and then the 2 falls under the critical depth, and then 4 falls under the uniform flow conditions, I mean, the normal depth. So that would be easily, because small q squared stand for the discharge per unit width and divided by the gravity to the cubic root. That's from the Manning's equation. So the velocity is determined pretty much like, you know, the small q divided by y, water depth. Right. And then in terms of the damping effect, so we use the Mendes and Losada 2004 model. As you know that when the wave propagates over the stem or the reed beds, of course, the wave height as well as the velocities are reduced. And then these are particularly, I think the Dr. Sultan mentioned yesterday about depend on the reed density, spacing, width, and also the flexural rigidity of the vegetation cover and so on. Again, so that's a typical model, the damping coefficient. So the nearshore wave height is determined through the offshore wave height, and then the damping coefficient, and then the shoaling coefficient. Right. So these are the sections we've been taken, and then what we have done actually, so we put all the models into a typical Excel spreadsheet, okay, very basic study, and then we calculated the known parameter, for example, like the velocities and so on. So what you could see here is a table with the different erosion zones from the 1 to 4, and also these are the typical hydraulic parameters, and then our main concern is the zone 2 and then the zone 4, where we have the fluid numbers over 1, which is supercritical flow. Right, and then we used Havlett et al. 2003 chart to get the permissible velocity against the exposure duration here. And there are 3 conditions, guys. So the one is actually that's a good, normal, and then the poor and so on. So that we have taken the worst case scenario here. And then, so these are the extracted information from the chart. You can see the limiting velocity and then the time. Now, quite important to get the exposure duration. So what we have done, we looked at the predicted against the monitored or the observed. That would be actually the surge. So we looked at the last 8 events in the area, 1993, 2013. That's our main concern and all these. So that, I mean, this is particularly about the overflow conditions. So we looked at the peak water levels, which is observed versus predicted, as I see here, I mean, as you could see here, and then the duration, pretty much that in terms of seconds, so that get the difference divided by that, so that would be the rate of change of, you know, increase in water levels and so on. And then we average it, so finally we have a quite average value in terms of the area, the rate of increase in water level. And for the case of overtopping, what we have taken the duration of exposure as 1 hour. So this is about the overflowing, right? Finally, you can see some. I'm really sorry that, I mean, you can't see any pastel shading here. The pastel shading, if you look at the pretty much the full paper, that would give you the sections where the overflowing, and also the bold sections are given by, so where the sections exceed the critical values like the permissible velocity as well as the exposure duration. So we calculate the percentages across, the differences you can see. So these are the exceedance, and then the negative will give you the subsidence and so on. Right. Just to conclude my presentation, so if you look at the levee structure would fail, this is the critical scenario with the overflowing, and then the section 1, the design scenario 1, which is the 100-year return period of water depth combined with the 1-year return period of the wave heights and so on. So that would be the whole section, 71%, 43, and then so on, and then the rest by wave overtopping. And also, as you see here, the plain grass reinforcement would fail in all scenarios as a good, normal, poor, and so on for the scenario 1, and then we have different figures for the scenario 2. The largest exceedance in velocity duration occurred in those scenarios you see earlier, the overflowing, and also for the wave overtopping was quite close to velocity exceedance for scenario 2 and 3, which could have resulted in failure had it not been for the presence of reed beds. Now, as I said before, there are some limitations for this particular MSc project. One of the things, because normally in ULs, the MSc is just on 1 year. So that 6 months for the project. So he has looked at 7 sections across 3-kilometer stretch. So we have never, or maybe we need to do some extent of the topographical survey. The next thing, we didn't look at the joint probability. That's one of the things we could do in future. And also some of the parameters we extracted through the photographic evidence, particularly about calculating number of the grass and density, and then stem height, width, spacing, and so on. The next thing about we looked at only the external hydraulic process rather than looking at the internal processes such as the geotechnical analysis, or maybe looking at the slope stability analysis. To acknowledge Lee Sensia, so at the moment he's working as a civil engineer, the water surface planning engineer, Essex County Council. Actually, I belong to Essex County Council. I'm based in my home in Essex. He has a plan to do a PhD, so I think he has done a very good job. And Mrs. Alexandra Murphy from Wallingford, Dominic Hames from Wallingford, Jonathan Sim, Technical Director from Wallingford, and also the Daniel from Environment Agency. Yeah, thank you.
So I just wonder that the grass covered surface is not strong enough against the flooding water.
That's right.
And why you still use these covers? If we use concrete covers, it is easy to solve the problem. Is it the traditional reason or the environmental issue, or what is the reason?
Exactly. I think it's what the Environment Agency wants, actually, they want to highlight the importance of using the reed beds. So, because that will actually definitely increase the environmental, the sustainability. So, if you look at the British, the embankments, these are normally earthen embankment rather than having the concreted. That's right. You're talking about wave action. Yes, I think because if you look at the numbers, these are actually around 2 meters. That's actually the offshore, and then when you do the transformation, so probably it would be, I would say considerably, compared to other places, because this particular, the tidal estuary is, one of the largest in the country. I would say that's around actually from 1 to 2. Okay.
So for practical application of your debris motion, it's necessary to include the concentration or the total amount of debris included in tsunami motion. So are there any way to evaluate the concentration or the total mass of debris?
Unsteady flow condition. Piece of unsteady conditions where the flow is not constant as here, and you can actually see that for unsteady flow sometimes there is a number of columns that are located and simulate the columns.
Well, my question is that for the case of Japanese coastal village, the buildings are made of wood, so there should be many debris after the first attack of tsunami. But if the structures are made of concrete, the number of debris is very limited. So these two differences should be included for the practical application. So it depends on the land use or what type of village are located in the coastal area. So this is a different topic. How do you think? Will it be possible?
Thanks, Nestor. Very interesting analysis. I observed that most of the tests that you have done is considering the straight impact of the tsunami inland with a flat beach, I would say, or flat platform, right? But when you consider some irregular topography, of course, you could have a different behavior of the tsunami. And maybe in that case, it's not wrong to think these very wide angles of 22.5 degrees. So when you consider the topography, because in Coquimbo, for example, 2 years ago, the tsunami entered in one side and then exited the city from the other side. So the debris were spread out almost parallel to the city. So parallel to the beach, I'd say.
actually, well, my question originally was sort of like around what Raphael was saying, and the explanation that you gave is very good. I'm just wondering whether you're planning to, I've been also in an office for several years, and I'm wondering whether you're planning to ask people to modify that 45 degrees, because I think that would be dangerous, because an engineer in an office is often not going to go to the effort to really look in that much detail of what's happening in the site and whether a wave can actually go into the side of a mountain, come back reflected in a different way, or some sort of funny behavior happening. And maybe that 45 degrees is a conservative and... Thank you very much for the question. When I started doing this work, I asked him to do some tests on concentration of flow. So what is the effect of flow restriction on standard has a provision, and this was not even part of his DOT. He put it in a with a lot of these unknown elements.
Okay, so Ravi, do you have, okay, very short question and short answer, Ravi.
Thank you, Ian. I think it's great, great piece of work. I wonder whether friction factor needs to be incorporated in the whatever this, the angle behavior.
Okay. So last presentation in this second session is will be done by Mr. Tomoyuki Takabatake, our secretary. So last presentation in this second session is will be done by Mr. Tomoyuki Takabatake, our secretary. So last presentation in this second session is will be done by Mr. Tomoyuki Takabatake, our secretary. So last presentation in this second session.
This seminar, and let me say I'm very happy to work as a secretary on this seminar. Then I'm going to talk about one of my research topics. The title is Advanced Approach for Tsunami Casualty Estimation. So this is the introduction. As everybody knows, the tsunamis are one of the most destructive type of natural hazard to coastal areas. So it is very important to quantitatively assess the potential loss of life that can result from tsunami to develop and prioritize effective countermeasures. Then previously, many approaches to estimate the number of tsunami casualties have been proposed. For example, some people have used GIS tools to assess the tsunami risks. And recently, many researchers have started to use a tsunami evacuation simulation modeling to conduct tsunami risk assessment. And this approach tried to consider the evacuation behaviors, and they provide us very important information regarding the tsunami risks for their study areas. However, these previous researches have still ignored many components of the intended evacuation behavior about risky individuals. For example, most studies have expressed evacuation start time for evacuees in a very simple way. What I mean is that they assume that all the evacuees start sometimes at the same time or follow just a simple distribution function, like a Rayleigh distribution function or something like that. But in reality, it has been reported that people have a variety of evacuation triggers that can prompt them to start their evacuation. I mean, some people start their evacuation after they feel the ground shaking, but some people start evacuation after hearing the tsunami warnings, but some people start evacuation just after seeing tsunamis or just after seeing other people evacuating. So these evacuation triggers should influence the number of casualties, but as far as we know, these evacuation triggers have never been considered in the tsunami evacuation simulation modeling, which attempts to estimate the tsunami casualties. And also, most studies have assumed that evacuees proceed to go to the closest evacuation place by the shortest route. For the case of local residents, probably it is okay, but for some coastal areas, there are so many visitors, tourists, when the tsunami comes. So generally speaking, visitors do not have enough knowledge about the study areas, about the areas. So it is also important to consider the presence and behavior of tourists or beach users. Of course, it is really, really difficult to express, to simulate human evacuation behavior perfectly. But if we can include the detailed evacuation behavior, we can understand the tsunami risks in detail. At least we can answer the question quantitatively, such as what kind of people are more vulnerable, what kind of evacuation behavior should be changed. We can answer these questions quantitatively. So in this study, we tried to propose an advanced approach for tsunami casualty estimation. This proposed approach is based on a tsunami evacuation simulation model that considers a variety of evacuation behavior. And I tried to incorporate such evacuation parameter as much as possible by analyzing the previous questionnaire survey results. So before explaining the proposed approach, let me talk about the study area in this study. I selected one beach, the name is Kamakura, and the location of the study area is shown with a red star. And this area has a high risk of tsunami and a large number of visitors and beach users throughout the year, for a year. And as you can see, the North American plate and the Pacific plate and the Filipino Sea plate meet approximately 300 kilometers away from the bay of the study area. And also the Sagami Trough and the Nankai Trough are also located outside of the bay, such like this. As a result, this area is surrounded by number of earthquake fault lines that would generate tsunami to this study area. So historically, this study area has experienced a number of earthquakes and tsunamis, and nowadays it is regarded as the most vulnerable areas for tsunamis in Japan. So from now, I'm going to talk about the methodology and the approaches to estimate the tsunami casualties. In this approach, I calculated the number of tsunami casualties based on the tsunami numerical simulation models. For the tsunami numerical simulation model, I use a simple, very simple simulation model. The governing equation is a general set of shallow water equations. And the tsunami evacuation simulation model. The model was constructed using the agent-based modeling platform, the named ArtSoc. This modeling platform enables us to depict the evacuation behavior in detail. And in this study, I tried to consider 3 types of agents, 3 types of people. First one is local resident, and second one is tourists, and also beach users. And their evacuation behavior and awareness and preparedness are incorporated into the tsunami evacuation simulation modeling by analyzing the results of previous evacuation behavior survey questionnaires conducted in this study area. So as I told you, in my simulation model, I tried to consider the evacuation triggers. Based on the results of a questionnaire survey, I categorized the evacuation triggers into 4 types. Namely, trigger 1, ground shaking, trigger 2, tsunami warning, and trigger 3, sea others evacuating, trigger 4, sea the tsunamis. And I assigned 1 trigger to each agent based on the results of a questionnaire surveys. So for the case of local residents, according to Enomoto, the local resident in this study areas answer that they would evacuate, 70% of the local resident answer they would evacuate after feeling ground shaking. And 74% of the local resident answer they will evacuate after hearing tsunami warnings. So I assigned this percentage to each agent. And I assume when this trigger event occurs, the agent who will respond to this trigger will decide to evacuate, and after the preparation time has passed, they will start evacuating. For example, if the people's trigger is trigger 1, they start preparation immediately after the earthquake. And after they finish preparation, they start actual evacuation. The preparation time is also defined based on the questionnaire survey results. For the case of local resident, again, I use the results of Enomoto. And for the case of tourists, I use the results of Carlos Sares. And for the case of beach users, I used Sugimoto et al.'s results. For the case of evacuation route choice, I also use the results of questionnaire surveys. I showed one example. For the case of beach users, according to Sugimoto et al., 9% of the beach users answered where they should go. They answer they will go to the designated evacuation place. So it is assumed that 9% of people know the closest evacuation place and shortest route to reach them. And also, according to Sugimoto et al., 61% of the beach user answer they will go to a higher place or go to a spatial place. So I assume that 61% of the beach users in the study area will go to the higher ground. And 21% answers that they will go to the higher building, and I assume they will go to a higher ground, and other people assumed to follow other individuals. So regarding the moving speed, I tried to consider the evacuation age and cloud densities. So in this evacuation simulation modeling, so older people move slower. And when there are so many people on the road, the evacuation speeds gradually decrease. I assume that. And as I said, I estimated the number of casualties based on the tsunami simulation modeling. I extracted the results of depth velocity product calculated from a tsunami numerical simulation model, and I used these values, to estimate the number of casualties. So I'm going to show you the result. As I showed you, this study area is surrounded by a lot of earthquakes, earthquake fault lines. So I selected 3 earthquake scenarios, Meiyo, Keicho, Genroku Kanto earthquake scenarios, because these 3 earthquake scenarios generate higher tsunamis to the study area. As you can see, this place is a study area. So this fault line is far away from the study area. In contrast, in the case of Genroku Kanto earthquake, the fault line is very close to the study area. So as a result, this is calculated time history recorded at the offshore point. The black line shows the results of Meiyo, and blue line shows the result of Keicho, and red line shows the result of Kanto. As you can see, because the fault line of Genroku Kanto is close to the study area, tsunami reaches faster than these 2 tsunamis. However, the tsunami height, as you can see, is much higher in the case of Meiyo tsunami and Keicho tsunami. So inundation process is also different, like this. This is Genroku Kanto, and this is Meiyo. Genroku Kanto inundate earlier, but Meiyo tsunami's inundation area is much larger compared with Genroku Kanto earthquakes. So I'm going to show you the results of casualty estimations. So in the simulation, the number of evacuees and the age distribution ratio of the evacuees was set based on the study areas census. As a result, totally around 20,000 people are located in the study area. I will show you the evacuation modeling result. So they will move according to the rule I said. Like some people start evacuation immediately after the earthquake, but some people will not start evacuating before they see tsunamis. So as you can see, by using this approach, we can estimate the number of casualties. So this is the result. This is a result of casualty numbers for Meiyo tsunami case, Keicho tsunami case, and Genroku Kanto tsunami case. As you can see, Meiyo tsunami caused more than 1,000 casualties and can be regarded as the worst tsunami scenarios compared with these 3 tsunamis for the study area. But as you can see, the Genroku Kanto tsunami, the number of casualties is smaller, but still significant number of casualties occur in this case as well. So this is results of the mortality rate summarized by the agent types. So as you can see, this is the mortality rate of the beach users. This mortality rate is around twice as high as local tourists' mortality rate and tourist mortality rate. So based on the result, we can say that the beach users are more vulnerable to Meiyo tsunami. And this is a result, again, the mortality rate summarized by the evacuation triggers. As you can see, this is a result of the mortality rate of local people whose trigger is ground shaking and tsunami warning, and these are the results of tourists whose triggers are ground shaking and tsunami warning, and these are the results of beach users. As you can see, many of the evacuees whose trigger is T1 or T2, I mean, if people evacuate after they feel ground shaking or after they hear tsunami warning, they survive from Meiyo tsunami case. However, in contrast, the T4 evacuees the people who evacuated just after seeing tsunami, the mortality rate is relatively high. As you can see, in the case of beach users, 94% of the beach users die. And if we look at the local resident result, we can find out that T3 local resident, the mortality rate of the T3 local resident is also high. This is because that some local resident is located very far away from the evacuation areas, evacuation roads. So which means that most of the local residents cannot see many people evacuating, which means that they have less chances seeing others evacuating. So that's why they cannot evacuate as soon as possible, and as a result, they became casualties. And this is a result summarized by evacuation route choice. So in this figure, let me focus on the results of each users. As you can see, the BC1, the mortality rate of the BC1 is relatively lower compared with others. BC1 is the mortality rate of the people who went to the closest evacuation place by the shortest route. So we can say that the visitors and beach users who know the closest evacuation place are more likely to survive from the Mayo tsunami scenario case. So let me summarize my study. So in this study, the advanced approach to estimate the number of tsunami casualties was proposed. Because, as I told you, the proposed approach is based on a tsunami evacuation simulation modeling that considers complex human behavior, awareness, and preparedness. So it can provide significantly more detailed information about tsunami risks than the previous studies. So we can answer quantitatively the question, what kind of people are more vulnerable? So I apply the proposed model to the study area, and I clarified that for the study area, it is very important, firstly, to consider the risk of beach users, because the mortality rate of the beach user was relatively higher in the case of Mayo tsunami. And it is also important to change the intended evacuation behavior of individuals who intended only start to evacuate after seeing tsunami. But we need to think about this. And, but in other words, if they evacuate immediately after the ground shaking or tsunami warning, they could survive. It is also important to think about this. And also it is important to ensure that local residents start evacuating on their own will without expecting to see others evacuating, because some local residents' houses are, as I said, far away from the evacuation route. So they might not have many chances to see evacuees. So they have to evacuate on their own will. And also it is very important to tell visitors, tourists, beach users, the information about evacuation places and the evacuation routes to reach them. And this is a further application of the proposed approach. By using this proposed approach, it is also possible to evaluate the effectiveness of tsunami countermeasures, like this. So this is results of no countermeasure. The mortality rate is almost like 9% or something like that. But if we consider the countermeasures here, we can decrease the casualty numbers. If we compare the difference of mortality rate, we can understand which countermeasure is more effective, which countermeasure can reduce the most the number of casualties. We can understand something like this. But lastly, I need to say this approach also makes considerable assumption of human evacuation behavior. So there are still likely to be significant gaps between the simulation and reality. So of course, further investigation about intended evacuation behavior are necessary. So thank you very much for my presentation.
Characteristic for the case of Kamakura was to include the tourists and also beach users. But for example, if you apply your model to Tokyo metropolitan area, downtown Tokyo area, are there anything else to be included for the behavior of the people in the area?
This is very good questions. I didn't think about this, but of course, in Tokyo metropolitan area, there are so many people, like tourists and not so many beach users, but how should I say? But anyway, we have to consider the local residents in Tokyo, how they will evacuate in the case of emergency. We have to think about more about the local resident, I think.
Okay, thank you. Any other question? Yes, please. Michael?
Which aspects of your modeling will you change if you want to simulate a tsunami event that will occur at night?
Sorry, occur at night?
Yes.
Yes, it is possible. It is possible, of course.
But the trigger mechanisms, you have 4. 2 of them are visual, seeing other people running and seeing the tsunami. Those will not happen during the night.
Yes, yes. Okay, so this case, I assume the tsunami comes at the daytime. But if we change like the percentage or something like that, we can, of course, apply this model to the night time. But of course, we need to think about more when we applying this model to the nighttime case.
Okay. Yes, please.
I was wondering, how do you validate all this behavior if you compare with a, I don't know, very simple exercise, for example? And I saw that you considered any person as an individual. What if you analyze the family, for example, because the behavior could be different when you live alone or you have family with 2 or 3 kids you have to take care of?
Thank you very much for really good questions. The first one is the validation. I, of course, finished the verification process. I checked the evacuation speed, something like that. Very simple model I already checked. But as you said, validation is really difficult. I need to, I'm now trying to compare the simulation result with the TOEFL results. And now, actually, I am talking with Dr. Esteban, and he met a Chilean student, maybe you might know, but that student has real evacuation data recorded from the mobile phone or something like that. So anyway, they have the real evacuation data. So I would like to compare the simulation result with the real evacuation data. But the validation is not so finished. This is my answer, first one. And the second one is the family problem. Yes, this is very important. So actually, in this model, the people moves individually. So I do not include the family's effect. But of course, it is very important. Yes, I need to improve this model to include the family's influence or something like that. Thank you very much for.
Okay. Any other question? Okay, please.
Thank you for your interesting presentation. And I have been thinking application of your research to storm surge, but inundation speed of the storm surge is not so high, then maybe not so meaning. But I think the combination of storm surge and flooding is very somehow produce high speed inundation. Then is it possible to apply your methodology to the storm surge and the flooding condition, river flooding condition?
Yes, it's possible, but we have to analyze the questionnaire surveys regarding the evacuation behavior of from the storm surges or something like that. But if we analyze the evacuation behavior in the case of storm surge, it's possible. Of course, maybe we can collaborate.
I'd like to so.
Okay.
Thank you very much.
Okay. All right. Okay, one more question. Ahmad?
Could we go, please, back to the slide where you explained the survey results
Okay. Is this one? Maybe this one?
Yeah, the one afterward.
This.
No, I think slide number 9. Yes, this one.
Oh, okay, sorry, this one.
So you said you assumed that about 61%, according to the survey results, will go to a higher ground, and another 21% will go to a higher building. So what's the end point for their motion? Like, for example, if I saw that tsunami, or if I felt the ground shaking and I was staying over there, and then I decided to evacuate to a higher ground, and I moved to the end of this hole, and then I got scared and decided, no, I will move higher. So what's the end point for their motion?
Okay, so maybe, okay, this is actually a very, very simple assumption. And I just assume that people will, okay, in my simulation model, I include the ground elevation height. So when the people comes to the intersection, they automatically compare the ground height, and they will move to the higher places. So this is the numerical techniques. But as you said, some people, and actually this behavior was observed in the case of Tohoku tsunami, some people go to the higher place, but some people started to feel it's not safe, and they change the evacuation places. So actually this kind of second evacuation process should be included in the future.
Okay, so, and then a very quick question. How do you define a beach user, or what's the distinct difference between a beach user and a local resident or a tourist? Like, isn't a beach user a mix of the two?
Beach user and tourist?
Yeah, like what's the distinct difference between a beach user and a local resident or a tourist?
Okay. So in this simulation, local resident is just the people who are living in this place. So that place, Kamakura, is really regarded as a very high-risk tsunami places. So people who live in this area have more knowledge about the evacuation places or something like that. So their evacuation behavior should be different, like from tourists and beach users. And you know, actually there is not so very big difference between beach user and tourists, but I felt that we should, you know, make difference, and we should use another evacuation process or something like that.
Yeah, I understand. It's still, there are some multiple aspects that you're considering. It's just that I didn't really understand the difference, and so I think that the local residents could also be on the beach as well as in their homes.
Okay.
And you know, the tourist could be anywhere. So
yes,
yeah,
yes.
good luck.
Yeah.
It's a bit complicated.
This place distribution should be considered more. Yeah, thank you. Yeah, definition. Okay. Mm-hmm. Yes. Yeah. Okay.
So we already finished all our presentations in this afternoon. And we would like to move to the panel discussion. And we will start, maybe it takes around 15 minutes to set the new arrangement of the chairs. So we will start from 4:15, okay? 20 minutes break. And please come back in 20 minutes.